So today we're going to look at another day of alternating series. And what we want to really concentrate and really understand is the alternating series remainder theorem, or it's also called the alternating series error bound. And so this first example, we're just going to jump into some examples. In this first example, we want to approximate the sum of the series by using the first 6 terms of this series that actually goes to infinity. So to write that, we're going to write S sub 6 for the sum of the partial sum of the first 6 terms. So that's going to equal sigma. And we're going to start at 1 and we're going to end it at 6 to get the first 6 terms. So n equals 1 to 6 of this series, -1 to the n over, and then 2n minus 1 factorial. Okay, so if we put, n plus 1 up here for the exponent. Okay, so if we put 1 in here, right, if we put 1 in here, that's going to give us an exponent of 2, which is going to cause this to be positive. So our first term is going to be positive, and we should recognize that this is going to be an alternating series right here. Okay, so then so we know it's going to be positive 1, so we might as well put that right now, 1 over, and if I put 1 in here, this is going to be 2 minus 1, which would be 1 factorial. Okay, so if we put the second one in here, that's going to cause this to be 3, which is going to cause it to be a negative. So I'm going to write minus for that negative, 1 over. And if we put 2 in here, that's going to be 3 factorial. And then if we put 3 in here, that's going to give me an exponent of 4, which is going to cause it to be positive. And so it's going to be plus 1 over. If we put 3 in here, that's going to give me 5 factorial. And then if we do 4, that's going to give me an exponent of 5, which is going to cause it to be negative. So minus 1 over. And then that's the fourth one. So 2 times 4 is 8, minus 1 is 7. So this would be 7 factorial. And there's definitely a pattern here to the denominators, right? And then the next one would be the fifth one. So this would be 6 for the numerator, and the power would be 6. And so that caused it to be positive. And then 1 over. And then if we put 5 in here, it'd make it 9 factorial. And so 1, 2, 3, 4, 5, and then we're going to do the sixth one, right? So to do the sixth one, this is going to be 7, right? So the exponent's going to be 7. So it's going to be minus 1 over. And if we put 6 in here, that's going to give me 11 factorial. All right. So this actually gives me 1 over 1 minus 1 over 3 factorial, which is 6. And then plus 1 over 5 factorial, and 5 factorial is 120. And then minus 1 over, and then 7 factorial. You may not know what 7 factorial is, so let's go to our calculator, okay? And let me show you. Okay, so 7 factorial, we type in 7, then alpha, window, and then number 9 is factorial. So it'd be 1 over 5,040. And then plus 1 over, and 9 factorial. Well, 9 factorial, again, we type 9 and then alpha, window, and then select number 9. And that would be 362,880. And then finally, minus 1 over an 11 factorial. And 11 factorial would be 39 million. Like, so they get big really fast, right? 39,916,800. So 39,916,000 and then 800. Okay, now we wrote every term out. We wrote out the first 6 terms. Okay, so you could take this fraction minus this fraction plus this fraction. We could do that, right? But we could also put this into our calculator and to get the actual summation for the partial sum of the first 6 terms, right? So this would be about, if we put the sigma notation. So again, on our calculator, we're going to press alpha and then window and then number 2. And we're going to choose x. Okay, so I'm in function mode, so that's why it's giving me an x. X equals 1 to 6, and then a fraction, and then we have -1 raised to the, and I'm going to type in x plus 1 because I'm in function mode, and then parenthesis, and then 2x minus 1, close the parenthesis, and then I gotta do a factorial on that. So alpha window 9. Okay, and if we press this, then this is the summation of the first 6 terms. Okay, so it's this whole decimal. So I'm going to write that whole decimal here. So it's 0.841147098446. And I'm sure it goes on. Okay, but that's the first 9 digits. Okay. So what does this mean? Okay, so this is the sum of the first 6, and that's an approximation for the sum. Okay, but how close are we, right? I mean, this sum that we wrote for the first 6 terms, is it far away from the actual sum, or isn't it? Okay, so one way we can do this is we can take the actual sum, whichever it is, minus the approximation that we did, which is s sub 6. And that's called our error bound, okay, or our error for the first 6 terms. And what we know is that this has to be less than or equal to the next unused term for a sub n, right? And a sub n is the absolute value of this, or in this case, it'd be 1 over the factorial. Okay, so that means this is going to be less than or equal to, so we use here's the first one, the second one, third one, fourth one, fifth one, sixth one. That means this has to be less than a sub 7, and a sub n is equal to 1 over 2n minus 1 factorial. Okay, now what is a sub n? A sub 7 in this case. So a sub 7 would be 1 over, and this would be 14 minus 1. So this would be 1 over 13 factorial. Okay, so this is what we got for our first 6 terms, right? So that means the sum, the absolute value of the sum minus the sum of the first 6 terms has to be less than or equal to 1 over 13 factorial. Well, if this is 1 over 13 factorial, then what that means is that this has to be in between negative 1 over 13 factorial and positive 1 over 13 factorial. So we can rewrite this absolute value inequality as negative 1 over 13 factorial is less than or equal to the actual sum minus s sub 6 is less than or equal to 1 over 13 factorial. And then we could add this s sub 6, which is this number right here, to this left side, the middle, and the right. And that's going to tell us what s is going to be in between. So let me slide my paper up a little bit. Okay, and so if we add s sub 6, right, s sub 6 minus 1 over 13 factorial, that has to be less than or equal to our sum, which is less than or equal to s sub 6 plus 1 over 13 factorial. And so this is going to tell us for this number, this term, our sum has to be in between these two values. Okay, so how can we do this? Well, we're going to take that sum that we did right there. I'm going to actually use the sigma notation. And then if we, because that's my sum of my first 6 terms, and I'm going to minus 1 over 13 factorial. And that's what we get. So our sum is going to have to be bigger than this number right here. Okay, so this value is 0.84 147 09845. Which is less than or equal to our actual sum, which is going to be less than or equal to, and then we have to do the same thing, but instead of subtracting minus 1 over 13 factorial, we're just going to add. So I went back up here and highlighted that and pressed enter, and that pasted it back in here. So I'm going to press plus, and we get this number, right? 0.84 147 09846. 8. So look, like what this means is that this sum that we got is really, really close, right? The only difference in these digits is this digit right here. This one, the lower bound is a 5 and the upper one is an 8. So, I mean, this sum for the first 6 terms is really, really, really close to the actual sum. And that's what it's telling us, okay? Now, again, to do this, all right, you wouldn't have had to write this remainder. That's just this little thing right here is called the remainder, this R sub 6. That's the difference between the actual and what we actually, the actual value and the approximation that we came up with right here for S sub 6. Okay. And then it's always going to be less than or equal to our next unused term. So that'd be the 7th term. Okay. All right, so that's how we're going to use the error bound theorem, and we're going to use it in some different ways today. All right, but that's one of the examples I want to look at. We did one similar to this the other day. Okay. All right, so let's go to the next problem. All right, for this next example, for part A, we want to use the alternating series remainder theorem. Okay, to determine the number of terms required to approximate the sum of the convergent series. So we know it's going to converge. Okay, with an error less than 0.001. So we want this error to be less than this, okay? And then we're going to use a graphing calculator with the summation features to determine the error, okay, or what the approximate value of the sum would be with this error, okay? All right, so for part A, okay, so what we know is that we have the actual sum, which in this case is 1 over e squared, okay? That sum minus S sub some big N. Now it's different than this N, right? It's just it's some number that we have to go out in order to approximate this within 0.001, okay? And so the absolute value of that, and what we know is that that has to be less than or equal to the next unused term. Well, if we're doing any of these, if this starts at 1, then the next unused term would be A sub N plus 1. Okay, and so for this, A sub N, okay, is the part that's without the alternating part of this. So we're going to neglect this. Basically, it's the absolute value of this. Okay, so that's 2 to the N minus 1 over N minus 1 factorial. Okay, and take a notice here that this is N minus 1, right? And the exponent here of 2 and the denominator with the factorial, they match, right? Okay, so what is A sub N plus 1, like this one, okay? So A sub, and this is a capital N plus 1, is equal to 2 to the, and this would be capital N plus 1 minus 1. So that'd just be this capital N, which is this sum that we have to go out. And then the same thing down here, but this would be N factorial. So N represents the number of terms that we're going to have to go out to. Okay. All right. And so this is called a remainder, this little term right here. So we could replace this with R sub capital N. We just don't know what the N is. Like the last problem I said, 6 terms, right? We just don't know what this number is yet. Okay. And we know that this is going to have to be less than or equal to A sub capital N plus 1. All right. And then now we know what this is. It's this, right? So that means my error, okay, has to be less than or equal to, and this 2 to the N over N factorial. Okay. So what this means is that this error has to be less than this number right here. Okay. So this is our error, and this error has to be less than or equal to this. So we're looking for what term, what value of N would cause this whole value to be less than 0.001. So we would write 2 to the N over N factorial, and that's going to have to be less than 0.001. So we're looking at the value of N that would cause this to happen, okay? So you start just jumping in, okay? So let's take a look at what would 2 to the third over 3 factorial give us, okay? And so that would give us an approximation of 1.333 3. So that's not less than this, right? So I knew that what I already calculated this, but if you looked at this, we could do 2 to the third over 3 factorial. I pushed the wrong button. So alpha window 9. And that's what we get here, right? Approximation. So it's not under this value. So let's jump quite a few ahead. Let's jump like 2 to the 8th. Okay, so let's jump to 2 to the 8th. So this would be 2 to the 8th over 8 factorial. And we're just trying to find one of these that's less than this. Okay, so we try 2 to the 8th over 8 factorial. And that gives us 0.006, which is not under the 0.001, right? So let's jump up to 2 to the 9th, because we're starting to get a little close, right? This is a lot closer than this one. Let's try 2 to the 9th over 9 factorial. Okay, so grabbing my calculator, 2 to the 9th over 9 factorial. And we get 0.0014. But that number, okay, so we got the 0.001, but it's not less than this, right? It needs to be less than this. So we're really, really close right now. So 0.0014, which is not less than 0.001. If we go to the next one, which would be 2 to the 10th over 10 factorial, I bet we'll have it, okay? So let's go 2 to the 10th over 10 factorial. And so that would be 0. Okay, so we got to move this 4 places over to the left. So that'd be 0.0. This would be 0.0002, which would be right under this amount right here. So we found it, right? So we know that when this n is 10, right? When n is 10, that's going to give us an error that's less than 0.001. Okay. So let's go ahead and, so we know how many terms we have to go out. We have to go out 10 terms. Okay. So let me write that down. So we need 10 terms of the series to approximate the sum of the series with an error of less than 0.001. That's what it would take. It would take 10 terms to go out. Okay, so let's figure out what this would be. Okay, so we're going to go sigma n equals 1 to 10, because we need to go out 10 terms of the same function we have above. So -1 to the n minus 1 power times 2 to the n minus 1 power over n minus 1 factorial. Okay, so we're going to put that in our calculator. Okay, and I'm hoping we get a fraction here. Okay, so alpha window, and then we're going to do a summation. Again, I'm doing, because I'm in function mode, it's going to give me an x instead of an n. It'll still work. Okay, so 1 to 10, and then our fraction bar, and then we have -1 in parentheses, and then raise that to the n minus 1, or in this case, x minus 1. Come back down out of that exponent, and then to raise to the n minus 1, or in this case, I have x minus 1, and then parentheses x minus 1, or n minus, which is the same as n minus 1 again, and then factorial. Okay, so let me try to get this as a fraction. Okay, and it gives us, so you can always go math. I should have done that slower. Sorry. If you go to math, and you can choose one to switch it to a fraction. Now, sometimes it won't give you a fraction, but in this case, it did. Okay, so it gives us a sum of 383 over 2,835. Okay, so 383 over 2,835. Okay, the actual sum from above is 1 over e squared, right? And so we will see that if we take this value right here and we take the actual sum, which is 1 over e squared, and the absolute value of it, minus 383 over 2,835, that's going to give us a number that's less than 0.001. So I'm going to put this in my calculator, and I'm going to show you that it'll give me that error that I'm talking about. So you understand what we just calculated, okay? We figured out how many terms it would take to give us this small of an error, okay? So if we go alpha and then window to pick up the absolute value, and then I'm going to type in a fraction bar and then 1 over and then e squared. And then minus this fraction that I had up here. So I see how I highlight it. And then if you press enter, it'll paste it in there. Paste it in the wrong spot though. And it's easier just to type it, I guess. Okay, let's get in here and let's insert. There we go. So I'm just going to type it 383 over. That's the only thing is with cutting and pasting. Sometimes if you want to put it in a really specific place, sometimes it won't do it for you. Okay. And so see, it gives us an error. Okay, so what is this? That means there's, that would be 0. So this value right here would be 0.000238281 and so on, right? But look, it's within 0.001. Now, if we'd only done the first 9 terms, it wouldn't have been this. We wouldn't be less than 0.001. So we needed 10 terms to get that close to the actual sum. Okay. So that's a way to figure out, okay, how many terms am I going to have to go out to approximate this? Okay. And of course, the more terms you go out, the smaller the error will be. Okay. All right. So let's do another one of these. So same problem, just a different series. Okay. So again, we're going to have to try to figure out, all right, what is it that would give us the right amount that would give us an error less than 0.001. Okay. So once again, we're going to look at this. So S minus S sub n, and it's this n that we're trying to figure out. And what do we know about this error? Well, we know this error is going to have to be less than or equal to the next unused term. So since we're starting at 1 and we're going to end it at 6 for the sum that we don't know this number yet, that means the next one would have to be a sub n plus 1. So if this is the 6th one, this one's going to be the 7th. If this is the 7th one, this one's going to be the 8th. If this is the 9th one, then this is going to be the 10th. Okay, a sub 10 would give us an error. Okay. So then we know that a sub n is equal to the absolute value of this. Okay, so that would take this -1 out, and we'd be left with 1 over n times 2 to the n power. Okay, and and this works because n is starting at 1 right here. Okay, this is called our remainder. All right, so absolute value of our remainder is going to have to be less than or equal to, and the next unused one, well, that would become 1 over n plus 1 times 2 raised to the n plus 1 power. Okay, and we know that this 1 over n plus 1 times 2 to the n plus 1 power is going to have to be less than 0.001 because of what's stated right up here. Okay, if we wanted to go 0.0001, then I would have to add one more 0, and we have to figure out what value of this is going to cause that to happen. Okay, so let's take a look at, okay, now notice something, that this number right here, the number right here we're multiplying by, and the exponent of 2 are going to match, right? So again, let's jump in and put a number here, the same number here and the same number here. Let's try 1 over 3 times 2 to the 3rd power, right? So we go to our calculator, let's see what that gives us. If it gives us less than 0.001, we found it, but we may have to actually go back up and go, okay, let's try it with 2 and see if that one does it. Oops, I have a glare right there. Okay, so let's try this one. So 1 over, I doubt this one works. Okay, so 3 times 2 raised to the third. Yeah, that doesn't give me less than 0.001, right? So this is equal to 0.04, not less than that, right? So let's jump ahead. Let's jump all the way to 6. Okay, so 1 over 6 times 2 to the 6. Now, if that's less than this, I'm gonna have to back up and try 5, right? Okay, if that's less than this, so I got to figure out the one that just barely gives me less than this. Okay, so 6, so 1 over 6 times 2 raised to the 6. And yeah, that gets me closer, but it's 0.002, right? Okay, so but I am going to try the next one. So let's try this one. 1 over 7 times 2 to the 7th. What does that give me? Right, because I'm so close, I might have it on this one. Oops, 7 times 2 raised to the 7th. And that's 0.0011. That's not less than 0.001. So I bet 8 will do it for us. Okay, so let's try 8. So 1 over 8 times 2 to the 8th. And see what that gives us. If that gives us less than 0.001, we have it. And it does, because that's, realize when it says e to the negative 4th, puts it in scientific notation. So that means there's 4 zeros before this, okay, before this 4. So that's why I know quickly I can go, okay, that's 0 point, that's my first 0, and then 1, 2, 3, and then 4, 8, 8, right? And just 0.001, that's smaller than 0.001. So that's the first one that's less than it, right? Now, what's in this spot right here and right here is n plus 1, right? That's n plus 1. And so what I know is n plus 1 is equal to 8, which means n has to be 7. So what does that mean? That means I'm going to have to go out 7 terms in order to get a sum that has an error that's less than 0.001. Okay. So we would need 7 terms. Of the series to have an error less than 0.001. Okay. All right. So let's find that sum. Okay. So it's going to be sigma n equals 1 to 7, and it's -1 raised to the n minus 1 over n times 2 raised to the n. Okay, so using the summation feature of our calculator, whoops, sorry, you couldn't see that. All right, so using the summation feature of our calculator, press alpha, window, and then number 2, and x equals 1, 2, 7, and then fraction bar. And then for the numerator, we have -1 raised to the n minus 1 power over, and then n, which in this case is x, times 2 raised to that power. And we press enter and we get 0. We get this number, right? But we're probably going to be able to get this into a fraction. So I'm going to press math and then number 1 to change to a fraction. And we are. So 909 over 2,240. And 2,240, which is about, okay, the 0.406. Okay. And up here again, this is the actual value. This is the actual sum. This sigma, or this series, actually converges, and it converges to this number. All right. And so if we take this number and subtract that one, take the absolute value of it, you'll see that it's less than 0.001. So I want to do that one more time. We don't need to write it down. Okay. But I'm going to do my absolute value again. So that's number one. And then I'm going to put this in. So that's ln of a fraction 3/2. And then minus the sum, which is 909 over 2,240. Okay, so this is the actual sum, and then this is the sum of the first 7 terms, and you're going to see that the difference between those is less than 0.001. Yeah, so like I said earlier, this is times 10 to the -4th. So that means this is 0.000 and then 3. So yeah, that's less than 0.001. Okay, so that's how you do these problems. Okay. All right. So the next thing I want to look at is go back and I want to look at conditional convergence and absolute convergence once again. Okay. Because that's going to be that's a big deal. Okay. All right. So let's take a look at the next one. So again, I want to look at this idea of absolute and conditional convergence. Okay. So if the absolute value of a sub n converges, okay, then we know that the actual series must or absolutely converges. Okay. All right, and we call it absolutely convergent. Okay, so both, if the absolute value one, the actual one will converge. Okay, now this one sometimes diverges, and then this one will converge. So if this one converges, but the absolute value one diverges, then we say that the series is conditionally convergent. Okay, and then the other thing that could happen is that you take the absolute value and that one diverges, and then a sub n also diverges, right? Because that could happen, and that doesn't mean anything. All right, it just means everything diverges. All right, so let's take a look at this, and remember, this is a good idea to see if a series converges. Okay, when there's negative and positive values in terms of in the series. So this is always a good test to know if the series converges or not. Okay, so this one's going to alternate because we have -1 to some power, right? And that power is changing, and sometimes it's going to be even and sometimes it's going to be odd. Okay, so if we take a look at this, all right, this series right here, we want to take a look at how does the absolute value of this series behave? Okay, so that makes this sigma n equals 1 to infinity of the absolute value of -1 to the n plus 1 power over n plus 1. Okay, so this is going to go away, right? So really, this is going to be, if we put 1 in, it's going to be 1/2. And then plus, because the negatives are all going to go away, right? So it's going to, if we put 1 in here, it'd be 1/2. And then plus, if we put 2 in, it'd be 1/3. And then plus 1/4. And then plus 1/5. And then plus ... And it's going to keep going forever, right? So another way of writing this is sigma. And we could start this at n equals 2, right? N equals 2 to infinity, because you could see that this is 1 over n, right? So, and I want to write it as 1 over n because then I can use the p series test, right? And so what do we know about this series? Well, this series diverges because for it to converge, p would have to be greater than 1, right? And so we know that this diverges by the p series test. Because p is less than or equal to 1. And whenever it's less than or equal to 1, it's going to diverge, right? All right. So what do we know? Okay, because this one diverges, that means this one must diverge, right? So the absolute value. So this is not absolutely convergent. But now we have to check for, is it conditionally convergent, right? So we know that n equals 1 to infinity, this original series, right, that we were really checking, -1 to the n plus 1 over n plus 1 diverges by the p series test. There's a lot of write-up on these. And P, we have to say P is, we have to state that P is less than or equal to 1. Okay, so this one is saying, this one right here is saying only this one's diverging, right? And then you got to state that, okay, this one right here, this one diverges. For the same reason this one is, because these are actually equivalent, right? Okay. All right, so now we're going to check, is the actual series converging, right? So if we look at the actual series, the terms of the series, right? Sigma n equals 1 to infinity of -1 to the n plus 1. Let's look at a few terms on this. Okay, so if we put 1 in here, 1 plus 1 would be 2. So that's going to make this positive, right? Positive 1 over, and this would be 2. And then if we put 2 in here, that's going to make this 3, which is going to make it a -1, which I'm going to write as -1 over. If we put 2 in here, it'd be 3. And then if we put 3 in, that makes this 4. So it's going to be positive 1 over 4. And then if we put 4 in here, that's going to cause the exponent to be 5. So then minus, and then 1/5, right? And you can start to see 1/2 minus 1/3 plus 1/4 minus 1/5 plus, and then 1/6, and then minus dot, dot, dot. Okay. And so our a sub n is equal to 1 over n plus 1, right? That's what our a sub n is. So the only other thing, I mean, because this is an alternating series, right? The only test we could use is their alternating series test. Okay. So what do we know about a sub n, right? So a sub n has to be greater than 0. Okay. So that means 1 over n plus 1 is greater than 0. And that's 4. And let me fix that. I put my inequality a little too close, right? So 1 over n plus 1 is always going to be greater than 0. Now, and that's true for n greater than or equal to 1, right? For all of these, right? 1/2, 1/3, 1/4, 1/5, 1/6. Yeah, those are all positive, right? Okay. Then we also need to show that a sub n plus 1, right, is less than or equal to a sub n. So we got to show that thing, right? And then we got to do the limit also, right, of this as n goes to infinity. Okay, so what do I know about this? Okay, so a sub n plus 1 would be, we're going to put n plus 1 in here for this n. So that'd be 1 over n plus 1 plus 1. And that has to be less than or equal to 1 over n plus 1. So this would be 1 over n plus 2, which is less than or equal to 1 over n plus 1. And this would be, this is always going to be less than or equal to this one, because this denominator is going to be larger than this denominator, which makes this fraction smaller than this fraction, right? And so this is true for, also for n greater than or equal to 1. And then the last thing we need to do is the limit, right? So we need to show that the limit as n approaches infinity of a sub n is equal to, and this would be the limit as n approaches infinity of 1 over n plus 1. Well, this is n gets bigger and bigger and bigger. This denominator gets bigger and bigger and bigger. So this fraction gets closer and closer and closer to being 0. Okay. So we established that the a sub each term without the alternating part, right, is going to be greater than 0. That the next term for greater than or equal to 1, the next term is always going to be smaller than the previous term, right? And if we take the limit as n approaches infinity, then it equals 0. Okay, so what does that tell us? By the alternating series test, this tells us that this series right here converges, right? So now we know that sigma n equals 1 to infinity of -1 to the n plus 1 over n plus 1 converges by the alternating series test. Okay, which therefore, okay, the absolute value of it diverged, but the actual series converged, which makes this series conditionally convergent. Okay, so that means this series sigma n equals 1 to infinity of -1 to the n plus 1 power over n plus 1 is, and let me slide it up, is conditionally convergent. All right, so that's again, that's how you show conditionally convergent. You check the absolute value of it, see if that one works. If this one is if this original one was convergent, we'd be done. Okay, and that's always good, right? But if it diverges, if we can show that that diverges, then we need to go back and check the original series still. Okay. All right, we're gonna check this on some other ones. All right, so we're given this next one. Okay, determine whether this series -1 to the n plus 1. So because n is starting at 1, that's going to alternate between -1 and positive, right? Negative and positive, right? So this is going to be an alternating series. We definitely know that, okay? And we have 2n plus 3 over n plus 10. Okay, so we could, you wouldn't be wrong in doing this, is trying to do the absolute value, right, of this and checking the absolute convergence of it. But if you notice, if we take this out, right, and we do the alternating series to see if this converges, right, if this doesn't converge, automatically the absolute value one wouldn't converge either, right? Because what we have is the absolute value one. If the absolute value one converges, then we know this series also must converge, and we'd be done, right? But if you look, we're going to have to take the limit as n goes to infinity of 2n plus 3 over n plus 10, right? If we do that, then we're not going to get 0, right? And we're going to get a number. And what that means is if you try to do a sub n with n going to infinity, the limit as n goes to infinity of a sub n, if that comes out to be a number, then that actually means this diverges, right? Okay, so that's the nth term test. So we got to realize, like, this is a problem where we could use the nth term test. Okay, so what we want to do is we want to, you can start with alternating series. Okay, and so we look at this. So sigma n equals 1 to infinity of, and I'm going to write this as -1 to the n plus 1, and then times 2n plus 3 over n plus 10. Okay, so we'd have to show that this is positive, that the next term is less than, and then the third part of the alternating series test is we got to make sure that this one goes to infinity, right? Or sorry, that the limit as n goes to infinity, that this one goes to 0. But we should know just by looking at this, it's not. It's going to go to 2, right? So kind of looking ahead, I know that a sub n is equal to 2n plus 3 over n plus 10. And if we do the limit as n goes to infinity, okay, of a sub n, that would be the limit as n goes to infinity of 2n plus 3 over n plus 10, which we could rewrite that as the limit as n approaches infinity. And this plus 3 and this plus 10 as n goes to infinity are insignificant. So this is 2n over n, which means we're taking the limit as n goes to infinity of just 2, which is 2, right? And if this doesn't come out to be 0, right, that's one of the 3 things for the alternating series test. I just started with this one, right? Then that means we can't use the alternating series test. But this tells us something too. By the nth term test, this tells us that the series diverges. And since this series diverges, right, then we're done. We're done. If you can show that this one diverges, we're done. Like all of them are going to diverge. Okay. So what we know is that this series, n equals 1 to infinity of -1 to the n plus 1 times 2n plus 3 all over n plus 10 diverges by the nth term test. And recall that the nth term test just says if you take the limit as n goes to infinity of the terms of the series, right, and it doesn't equal 0, okay, then you know it diverges, right? If this doesn't come out to be 0, then it diverges. Okay, so it's really a test for divergence, not convergence. Okay, diverges by the, and I need to finish this, nth term test, and we're done. So so this one is a perfect example of, okay, if you tried the absolute value one, it wouldn't be converging, right? And then the actual series also doesn't converge, so they both diverge. All right, so that's it. Let's go to one more example. So what I'm trying to do is throw a lot of different examples at you, so you see how you can use these different tests. Okay, so each of these is different today. Okay, so again, I want to determine this one: is it conditionally convergent, is it absolutely convergent, or does it just simply diverge? Okay, so writing this out. Okay, looking at the first few terms, n equals 1 to infinity of -1 to the n, and then e to the negative n squared. Well, really, this means 1 over e to the n squared, right? So sigma n equals 1 to infinity of -1 times, and this is really 1 over e to the n squared. So let's write out the first few terms in this, okay? So if we put 1, oops, I forgot the n right here. So if I put 1 in here, right, then that's going to be -1. So the first term is negative, and then I'd have 1 over e to the 1 squared, which would just be 1 over e. And then if we put 2 in, that's going to cause this to be +1, right? So we're going to put a plus 1 over, and this would be e to the 2 squared, which would be e to the 4th. And then we put 3 in here, that's going to make it -1 over, and then be e to the 9th, and then plus 1 over e to the 16th, and then minus, and then ... This would just keep continuing, right? So what if we take a look at this one, and let's take a look at just the absolute convergence of it. Let's check for this if it converges absolutely. So let's take a look at sigma n equals 1 to infinity of the absolute value of, and then we'll do -1 to the n, and then times, I'm going to write like this, 1 over e to the n squared. Okay, so this -1 it's not going to be there, right? Because we're taking the absolute value of it. So really, this is going to be 1 over e plus 1 over e to the 4th plus 1 over e to the 9th plus 1 over e to the 16th, right? And so the absolute value, okay, so this becomes really, we could write this simpler than, and we wouldn't even need the absolute value, is we could write this is the same as n equals 1 to infinity of 1 over e to the n squared power, right? Okay. So, all right, we need to look at this. What is something we can use to determine whether this series is either converging or diverging, right? And okay, so e to the n squared, we actually could compare that to something else. Okay, this power, right, is going to cause this to be a pretty big denominator, right? What if we looked at this series? Okay, so let's look at this series, n equals 1 to infinity of 1 over e to the n, okay, or lowercase n. Okay, so because this is a 1 up here, you could actually write this as sigma n equals 1 to infinity of 1 over e to the n power. And we should recognize this as a geometric series. So yeah, this is a geometric series. And what's 1 over e? Well, it's between -1 and 1, right? So that means this converges by the geometric series test. So in this case, r is equal to 1 over e, and -1 is less than r, which is less than 1, right? So for a geometric series to converge, your r, your common ratio, has to be between -1 and 1. Okay, how is that helpful? Okay, so what we need to do is we compare this one to this one. Okay, so this is one of those comparison tests. And I'm going to do direct comparison test. So what does the direct comparison test say? Well, this 1 over e to the n, right? We know that one converges. And we know this denominator, right? Or this denominator is going to be smaller than this one, which makes this fraction smaller than this one. So what we know is 1 over e to the n squared is going to be less than or equal to 1 over e to the n power, right? And recall that by the direct comparison test, that if the bigger one converges, then the smaller one must also converge, right? All right. So by the direct comparison test, we know that this one, by rewriting this as 1 over e to the n and showing that this one converges, and then showing that this one is bigger than this one, right? Then that's telling us that this one converges, okay? And that's by the direct comparison test. So now we know that sigma n equals 1 to infinity of 1 over e to the n squared, right? Now, so we just showed that this one converges, right? Which in turn means this one converges, okay? So this one converges by the direct comparison test. And since this one is the same as this one, n equals 1 to infinity of the absolute value of -1 to the n times 1 over, I just realized you can't see it, sorry. N equals 1 to infinity, absolute value, -1 to the n over 1 over e to the n squared converges by the direct comparison test. Which tells us the original series also converges, right? And because this one converges, we don't even have to prove that the original one converges, right? We can just say it converges absolutely, okay? So we now know that sigma n equals 1 to infinity of the original one, -1 to the n, e to the -n squared converges absolutely. Or we can also say is absolutely convergent. You could say it either way. Okay, that's just two different ways of saying the same thing. Converges absolutely or is absolutely convergent. Same thing. All right. All right. So I want to do one more of these with you just to get more practice in. And so you can see just a variety of different problems where you have to use these tests. Okay. So for this last example, okay, we want to determine whether this series converges conditionally, absolutely, or diverges, okay? So let's go right to checking the absolute convergence of it, okay? So sigma n equals 0 to infinity of the absolute value of -1 to the n over 2n factorial, okay? And so really this -1 to the n is going to go away, right? Because we're taking the absolute value of it, and that's what's causing the alternating signs. All right, so if we put 0 in here, this would be 2 times 0, this would be 0 factorial. Now this is a weird one, right? What is 0 factorial? It's actually 1, okay? But this would be 1 over 0 factorial, and then plus, and then we put 1 in here, and it'd be 1 over 2 factorial, and then plus, and it's going to be 1 over, so we put 0, 1, and then we put 2 in, that'd be 4 factorial, and then plus, and then we put 3 in, and that would be 1 over 6 factorial, right? And we could keep going plus dot, dot, dot. All right, so this could be rewritten as the series sigma n equals 0 to infinity of just 1 over 2n factorial. Okay, so really right now, the only test we could use is some comparison test to this. Okay, so because this isn't because of the factorial, it's not a geometric series, it's nothing like that. Okay, there's actually gonna be a test called the ratio test I'm gonna show you, and that's not gonna be the next lesson. And I think that's that would help you with a series like this. Okay, so what we could compare this to is a p series, and I would do 1 over n squared. Okay, now why I'm going to do that, and that's the hard part of this, is I know that 1 over n squared is going to be larger. Factorials are going to be larger than powers. Okay, these are going to grow faster than anything else. Okay, so if you look term by term, 1 over n squared, right? These numbers are actually going to grow faster. Okay, so if we look at this series, sigma n equals 1 to infinity, 1 over n squared, we automatically know that this one converges by the p series test. Okay, now let me write out, okay, so the first few terms, this would be 1 over 1 plus 1 over, this would be 2 times 1, which is 2, and then plus 1 over, and remember, this would be 4 times 3, right? 4 times 3 is 12, and 12 times 2 is 24. That'd be 24. Versus this one, if we put 1 in, right? This one would be 1 over 1, right? And then plus, and then 1 over, and we put 2 in here, so 1 over 2 squared, that'd be 1 over 4, right? And then plus 1 over, and then we put 3 in here, this would be 9, right? So look at the first 3 terms, okay? So 1 over 1, 1 over 2, 1 over 24, but this one's 1 over 9, right? If we go one more, right? 6 factorial, that'd be 6 times 5, 30, right? Times 4, which would be 120. And I just went blank. Let's just do 6 factorial on the calculator. All right. So 6 factorial is 720. So the next one would be 1 over 720, where this one would be 1 over 16. So you see how this one's growing way faster. Okay. All right. So what we would say here is that 1 over 2n factorial is going to be less than or equal to 1 over n squared, right? And so we've established that this bigger one is converging. That forces this one to converge, right? So what we now know is that this one converges, right? So we could write like this: sigma n equals 0 to infinity, the absolute value of negative 1 to the n over 2n factorial, which happens to equal sigma n equals 0 to infinity of 1 over 2n factorial. And this one would converge by the direct comparison test. All right. And now, because this one's converging, we know the original one converges absolutely, or is absolutely convergent. So we could say sigma n equals 0 to infinity of negative 1 to the n over 2n factorial converges absolutely, or is absolutely convergent. You could say it either way. All right. Okay, so this was a lot of work on error bound, that alternating series error bound, and then also absolute and conditional convergence. All right. And so that's it for today. All right.